my pleasure as the Vice-Chancellor and President of the University to welcome you here tonight on behalf of the Hawke Centre and the University to Cancer Immunotherapy Here at Last with Professor Ian Fraser AC. The Hawke Centre is committed to the delivery of a diverse set of programmes and exhibitions throughout the year which reflect on our fundamental themes of strengthening our democracy, valuing our diversity and building our future. And this evening we're very happy to be joined by members of the University Council as well as our distinguished guests, our colleagues and our friends. In particular, I'd welcome Philip Marshall, who's the CEO of Oncology Research International Limited, Michael Brown, the Director of the RAH Cancer Clinical Trials Unit at the Royal Adelaide Hospital, Professor Greg Goulall from the Centre for Cancer Biology, where he's the Head of Gene Regulation Centre there, and Jenny Hughes, the Chief Executive of Seniors Information Service. Thank you all for joining us, and thank you all, ladies and gentlemen, for being here with us tonight. Now, many of you would know by now, if you don't know, you've probably had your head under a rock somewhere, that the University of South Australia is celebrating its 25th birthday this year. And throughout that year, we have organised any number of events to celebrate that milestone in the growth of a young and dynamic institution. And they range from the very obvious, like black tie gala dinners to raise funds for scholarships and campus parties where we give free food to the students, all the way through to more serious side of our celebrations and a series of public lectures throughout the year. The iconic public lecture series continues the university's mission to explore ideas and solutions for a sustainable 21st century. In tonight's lecture, we will hear the story of a man who was driven by curiosity and the need to do good for people. And the results of his efforts so far are 4 vaccines for the prevention and treatment of cervical cancer. Cervical cancer affects 500,000 women each year, and Professor Ian Fraser AC spearheads research which has the potential to eradicate this disease within a generation. Dr. Fraser is my favourite type of medic, a clinician scientist who's trained as a clinical immunologist in his native Scotland. Having earned a degree in medicine and in surgery, he trained as a renal physician to investigate the immunological issues around transplantation. And at that time, and this was back in the 80s, the place to study immunology was at the Walter and Eliza Hall Institute in Melbourne. And so a move and an extraordinary career began. It started with an investigation of how the immune system clears the hepatitis B virus. The study group that Ian chose was a group of homosexual men, a population with an unusually high rate of chronic Hep B. He soon learned that similar cases of immune impairment were appearing throughout the world, and that condition became known as acquired immune deficiency syndrome. Ian Fraser was among the very first to confirm that AIDS was common in Australia, and that was before a virus was associated with the disease. He and his colleagues suspected a viral origin, so they tested a cohort for a variety of viruses known to cause immune problems. They tested for a recently identified virus, HTLV-111, which later became known as HIV. And their work contributed to the growing body of knowledge that identified HIV as the causal agent in AIDS. It didn't take long to make the next connection. Dr. Fraser and his colleagues were the first to notice that AIDS patients often had significantly difficult issues around genital warts, which are caused by the human papillomavirus, or HPVs. Ian became convinced that the immune system played a role in the ability to protect against HPV-linked cancer, and that immunosuppressed patients, such as the victims of HIV, couldn't clear the virus, and the resulting uncontrolled HPV infection led to cancer. That connection and the next step would be to grow the virus in a lab and look to develop a vaccine. But HPV was a bit stubborn and wouldn't grow. And on a sabbatical at Cambridge University, Ian met virologist Jian Zhou, and they decided that if HPV wouldn't grow for them, they would create their own version of HPV and grow it regardless. Much hard work later, it's great how you can shrink an amazing career into just a few pages, isn't it? Much hard work later, out of that collaboration and their research at the University of Queensland, came the vaccine Gardasil, which is used primarily for the prevention of HPV-associated cervical cancer. Cervical cancer is the second most common cancer in women, and Gardasil has now been administered to more than 125 million doses in 121 countries. It is a true translational research story and a global success. Dr. Fraser is now the head of the Translational Research Institute, the TRI, a joint initiative between the University of Queensland, Queensland University of Technology, the Mater Medical Research Institute and the Princess Alexandra Hospital. It's Australia's first translational research facility which is dedicated to taking scientific discoveries into application for medical practice. Ian is continuing his research in immunoregulation and immunotherapeutic vaccines, supported by several US and Australian research funding bodies. He's working on a VLP-based vaccine, that's virus-like particles for the uninitiated, against hepatitis C. And he's also researching extensions to the VLP production technology for dengue fever and for Japanese encephalitis vaccines. Dr. Fraser expects a 50% effective HIV vaccine to be available by 2028, and he's already overseeing trials of the first vaccines for skin cancers caused by HPV, aiming to land those before 2020. For his work, he has been rightly recognised globally. He was nationally the Australian of the Year in 2006. He won the Prime Minister's Prize for Science in 2008, became an Australian Living Treasure in 2012, and was made a Companion of the Order of Australia in the 2013 Queen's Birthday Honours List. He and Dr. Zhu even went on to win the research equivalent of an Oscar. This is awarded by the European Patent Office, and it's voted on by members of the public after categories are chosen and nominated by a scientific panel. The European Patent Office President, Benoit Battistelli, noted that Ian and Zhu had received a staggering 32% of the nearly 50,000 votes cast online. I'm sure you will agree that that's somewhat of the icing of the cake on a truly formidable list of achievements. So ladies and gentlemen, it gives me great pride and pleasure to introduce our keynote speaker for tonight, Dr. Ian Fraser, AC.
Well, first of all, I'd like to thank you for the invitation to come and speak here this evening. I feel after that introduction that I'm probably not going to match up quite to the image that's been painted of me. But what I'd like to do for you this evening is to take you on a journey, if you like, starting with the problems that we face in health and ending up with some rather specific solutions to them. The building that you see in the picture there is the Translational Research Institute in Brisbane, a $350 million enterprise funded largely by state and federal government money, but with a very generous donation from Atlantic Philanthropies. And it now houses 650 research scientists. But what's really unique about it is that not only does it have the facilities for doing the basic discovery research and the translational and clinical research that eventually leads to products getting out there, but it also has the manufacturing capacity in the middle to actually make the products so that you can go literally from an idea all the way through to delivering a product to the public, all within the same building. And to my knowledge, that at least at the moment is unique for Australia and possibly worldwide. So that was the concept that got the place going. But actually, it's just really a very nice place to work. And the place that you're looking at there is the coffee shop, and that's our outdoor area. Let's go back to the beginning. This gentleman, Sir William Osler, is, if you like, the father of modern experimental medicine. He divined the way that we had to go about medicine if we wanted to learn, and he basically said that it was important to study patients, which is not a bad idea. He published a book, The Principles and Practice of Medicine, which has been around for a very long time, and the last edition that he was involved with was still recommending bloodletting, which kind of shows how slow we are in getting new ideas out into medical practice, and that's always been one of our challenges. But one of his recommendations is one which certainly would raise the eyebrows of some of you, I'm sure, because he envisaged a college where men would, and I note men, would retire at the age of 67, and after being given a year to settle their affairs, would be peacefully extinguished by chloroform. Those of you who are smart and quick will notice that he didn't quite follow his own precepts, because he managed to last to 71 years himself. However, what he defined was this business of thinking about medicine as something that you do experimentally. One of the challenges that we face is identified in this. We really have a problem with healthy aging now. When this cartoon was drawn on a temple in Komombo in Egypt, and what you're seeing in the picture on the right-hand side there is not the instruments used to build the temple, but rather the instruments used to extract bladder stones from the bladders of patients. At that time, the average life expectancy was about 45 years, and this 5,000 years ago. And it stayed that way for nearly all of those 5,000 years. In other words, all of the medical research, such as it was, that was done up to about 1840 made no difference to our life expectancy. As you can see from the graph here, what you're actually seeing is that between 1840 and about 1920, we gained about 20 years of extra life due to two revolutions, not the French and the American revolutions which occurred at that time, but the agricultural and industrial revolutions, which gave us safe food and water. And these public health measures gave us a lot of extra years of life. Controlling infections through vaccines and antibiotics added another 15, and all the rest of the benefit of research is just that little bit up at the top that now enables us to live to an average of about 85 years. But that's actually not the point. The point is not about how long we live, it's whether we live a healthy life as well as a long life. And that's where medical research really contributes. We have a challenge in this, that we do not manage to distribute our knowledge about medicine equally across the planet. The countries in dark green on the map there are countries where, like Australia, we have average life expectancies over 80 years. But the countries in black and dark red there are countries which haven't really changed their life expectancy since that temple was built in ancient Egypt, and the average life expectancy is under 50 years. And even within Australia, while we managed to, on average, do better than 80 years, our Aboriginal communities are still living 17 years less on average than we are. In other words, even within our own country, an advanced and well-civilized country, we cannot deliver the benefits of health and medical research effectively to our own people. There are distribution problems. One of the challenges that we face is that the cost of healthcare is increasing steadily. The orange line on that map shows the annual growth in healthcare costs over the last 45, 50 years in Australia, and the dotted green line, the average growth in productivity in the country. These are the sort of graphs that federal treasurers really like when they're arguing for more taxes or whatever. But the reality is that we're spending more and more of the money that we earn, more and more of the productivity of the country on healthcare. And it's not just us that's doing that. If you can see from the table there, you can see that this problem is a worldwide problem. And most countries in the world now spend about 10% of GDP, 10% of their wealth, if you like, each year on healthcare. And in almost every country, that's increasing steadily. So that's a real problem for us, because we cannot sustain the growth the way we're doing unless we can actually make some economies somewhere in the health system as well. So economists love to think that the whole thing is all about outcomes and cost effectiveness, and they draw graphs like this, which basically says that it's really quite a good idea to do things like vaccination and public health things, which don't cost very much and give a lot of benefit. And then our health minister looks at the other end of the graph and looks at the lost and unnecessary diagnostic tests and the adverse drug reactions, where in fact we're getting bad value for money because we're actually spending more and getting less back. But that's not really the way that we see healthcare, I guess. I mean, what we really look at is much more to do with the societal rather than the economic aspects of it. We want basically to get a healthy life out of the system. We want to get all the benefits that healthcare can deliver. So what are the challenges for that? Well, the problems are that we are faced with a number of chronic diseases. So this is really the problem. In the old days, it was infection, and we got over them and got better, but now we're faced with a series of chronic diseases, which are basically the 21st century problem that we've got to face up with. We live a long time, but we get a lot of problems. Cancer being the top on the list, and it's mostly cancer I'm going to talk about today. But we must also remember, by the way, that infections have not gone away, and that our ability to use antibiotics to control particularly bacterial infections is diminishing rapidly as resistance spreads widely through the bacterial community. So that we're going to have to think about infections as well. And that's fine, because that combines both of my interests. I'm interested in vaccines to control infections, and I'm interested in cancer. And what I'm going to do for you for the rest of this evening is try and put those two ideas together. And we shouldn't forget rare diseases. I mean, rare diseases are only rare if you don't have them. If you're unfortunate enough to get a rare disease, one of the problems is that it's unlikely that people are going to put a lot of effort into trying to protect you against those rare diseases, because we tend to prioritize our health research in the areas where the greatest demand is, and that's natural. What I will argue for, therefore, is remember that you never know where research is going to actually produce a benefit. The research that you do on something may lead to a solution for a rare disease that you never even thought was important, simply because research is largely serendipitous. We do things and we make discoveries, and then we work out how to apply them. Anyway, I'm going to focus on cancer and point out that that's because it is a disease of aging. The graph there basically shows that as you get older, your chances of getting cancer increases. It's interesting, right at the very end of the graph there, you'll see that your chances of getting cancer starts to diminish if you get past the age of 80. It's not just cancer risk that starts to diminish. Your chances of dying tomorrow start to diminish if you get past the age of 80 as well. That might sound a bit counterintuitive. Unless you think you're kind of special, it works just the same for fruit flies. Fruit flies that get past a certain age are more likely to die, are less likely to die tomorrow too. What it really says is there are genes that we have. Certainly we're genetically programmed to live a long time, and we're genetically programmed, some of us, not to get cancer. And if you survive long enough, then you're one of the elite that will continue to survive. It doesn't give you eternal life, I'm afraid. It just means that you're going to live slightly longer than everybody else. But cancer is a big problem. It's the commonest cause of death in Australia now. 1 in 2 of us will get cancer in our lifetime. 1 in 5 of us will die of it. And that will become a problem worldwide as infectious disease gets controlled across the rest of the planet. The good news, of course, is that we can cure cancer. 50% of cancers can now be cured. When I was a medical student, it was about 15 to 20%, and that's the benefit of the medical research that we've had over the course of the last 50 years. More importantly and more practically, we can prevent over 70% of cancer with existing knowledge, so long as we go about it in the right way. So there's a little public health message coming now for your benefit, and I want you to think and remember about it. So what determines whether we get cancer? Only 10% of your risk of getting cancer is what you inherit from your parents. You've got to choose your parents well. My parents have managed to reach the age of 90 now, so that's good for my potential survival. But my mother's had cancer 3 times, and therefore I've not got the right genes to avoid getting cancer, even though my mother has done well. But it's our environment and what we do to ourselves that's the problem. I'll come back to what we do to ourselves. The little gentleman down at the bottom there is doing one of the things that you should be avoiding, obviously. And all the things that we do to ourselves provide about 30% of the risk, and that's clearly avoidable. What we do to our environment is equally avoidable. And the diesel particulates out in the air out there on North Terrace are not good for your health and promote lung cancer much more than smoking does in terms of the number of cancers in this country. And if you go to China, you'll realize why it's a big problem there. But it's not just diesel particulates in there. It's arsenic in the drinking water in Central Asia. It's radioactive material in the environment that we release where we shouldn't. And all of these environmental factors contribute about 30% of the cancer burden. And then on top of that, we have the problem of viruses and bacteria that cause cancer. And it's mostly about that I'll speak this evening. But just as the public health message, just remember that we want to try and minimize our risk personally as well as wait for others to solve the problems for us. The problem that we all have is that we get these messages in the newspapers about what you shouldn't do, and the messages do get confusing. I mean, the front page of the paper says that cancer is caused by drinking too much coffee, and then on page 6 of the same newspaper you'll find an article that says that cancer is prevented by drinking coffee in another place and time. And we really want to have a very convincing set of messages, rather different from these rather confusing ones in a park in Russia, where basically some of the messages are pretty clear. You're not allowed to take your dog there, and maybe dancing isn't allowed in the park. But what the second one down on the left's all about is not clear. The second one down on the right is actually a message for the Australians that go to Russia, because it basically says you shouldn't keep your red wine too close to the barbecue. So that we want consistent messages, don't we? And these are the consistent messages, and the reason why I'm wanting you to follow them. You have to stop smoking if you smoke. Globally, the biggest challenge for cancer prevention is smoking. In Australia, we spend $31 billion out of our health budget on treating the consequences of smoking, and smoking kills 15,000 of us every year. These are figures from the Australian Institute of Health and Welfare. I didn't make them up. Maybe they did, but they made them based on surveys. Controlling obesity in the developed and the developing world is a significant problem for cancer risk as well. 10 cancers are increased in risk by the fact that you're more than 10% overweight. And the annual cost of obesity, not just the cancers caused by obesity, but obesity in general to Australia is $21 billion every year, with 5,600 avoidable deaths. Drinking less alcohol is never a popular topic, especially in the evenings, and it's not popular with me either. But just remember that alcohol is a class 1 carcinogen. That puts it in the same category as plutonium. Alcohol drinking in this country costs us $15 billion in healthcare budget every year and costs 3,200 avoidable deaths. And then sun exposure, well, maybe not in Adelaide, you're not quite as sunny as Brisbane is, but it looks pretty sunny out there, and $10 billion mostly spent on the skin cancer that I'm interested in, squamous skin cancer, the common one. $10 billion treating that every year, and 3,600 avoidable deaths, mostly from melanoma. So this, basically these 4 rules, and if you do your sums, you save about 1/3 of the healthcare costs of this country and about 1/3 of cancer deaths. So worth considering, I think. So when prevention fails, we've got to think what we can do for cancer. And I'm going to talk about one mode of treatment for cancer tonight, but I'll just remind you of the others. Surgery is your best hope of getting rid of a cancer if you've got it. If you can cut it out entirely, then it probably won't come back. And radiotherapy is equally capable for some cancers of curing you. These 2 modes of treatment have been around a long time, and they are effective. Chemotherapy is relatively newer. This is basically using poisons which are slightly more poisonous for the cancer cells than they are for the rest of you. And they are rarely a cure for cancer. They are a means of delaying the inevitable, but there are only a few blood cancers that are truly cured by chemotherapy, so that they are a sort of second line of treatment. But the one I want to talk about is immunotherapy. That's using the body's defenses against infection to fight cancer. And this is relatively new. And I mean, there are 4 little cartoons there, but the bottom line is that as I'll show you in a moment, we have ways of using the immune system that were not really thought of until quite recently. The immune system exists to fight infection. It's evolved with that in mind. But to the immune system, an infected cell and a cancer cell look very similar. And if we turn up the immune system, and we can do that by giving drugs which basically mimic proteins that your body makes itself to fight infections better, or if we take the brakes off the immune system by getting rid of some of the things that turn off your immune response when you don't need it anymore, then there is the potential to drive the immune system to fight cancer, as I'll show you. It's an idea that's been around for a very long time. This gentleman, William Cooley, who's the picture on the left there, treated the gentleman on the right who had a nasty cancer in his neck with a rather adventurous therapy back in the 1890s. He gave the guy live bacteria in large doses, and the cancer melted away. And this was Cooley's toxins. Now, it was toxic. He killed about 1/3 of the patients that he treated with this, but some chemotherapy is not much better than that. And the important thing was he cured almost half of all the patients he treated with that. He selected his cancer patients. It wasn't for every cancer, but for the cancers he chose, which were the ones which he recognized were able to be treated that way, he got good results. The reason this did not become popular was not because of the death rate from the patients with the toxins, because he actually learned not to use live bacteria, and dead bacteria worked just as well, and they didn't kill patients. The reason he didn't have a success was he was in the wrong place at the wrong time, as is often the case with medical researchers. He found himself in New York at the same time as Madame Curie was promoting radium therapy for cancer. Now, radium therapy was regarded as clean and green, whereas bugs were regarded as dirty and nasty. And Madame Curie won over William Cooley in terms of catching the affection of the doctors in New York. Of course, Madame Curie died of her clean green radiotherapy that was poisonous enough that she developed cancers from the radium therapy itself. So that perhaps William Cooley would have been a better bet, but that's the way that science works. At any rate, immunotherapy, as described by William Cooley, is actually the basis of immunotherapy as we do it now. We just don't use dead bacteria quite the same way. So this is Sir McFarlane Burnett, a very famous Australian, and he was famous for defining, first of all, the way that the immune system would work. He was a great theoretical immunologist, and really quite an outstanding character for a number of reasons. But one of his ideas was that if the body could fight infections with the immune system, should be able to fight cancers too. And basically, that was a dogmatic statement it made with no evidence at the time, but we now recognize that each of the tenets that he put forward have turned out to be true. First of all, the idea was that the immune surveillance, your body would prevent you from getting some cancers. And we now know that's true, because if you take away the immune system with drugs, say if you have a kidney transplant, you're more likely to get cancer for some sorts of cancer than if you hadn't had the drug. Statistically, the community will get, on average, about 3 or 4 times as many cancers if they're heavily immunosuppressed as for age-matched normal individuals. So the immune system is working in your favor all the time, even right now. The second thing that he proposed was that tumors would be different from the rest of us, in the sense that the cells would have something in them that wasn't our cells. And that's absolutely correct. We now recognize that some tumors have viruses causing them, like papillomavirus, the cervical cancer virus, and the virus proteins in the cancer cells are definitely not something that's part of you, and therefore something that your body's defense against infection can fight. But even cancers that don't have a virus, that don't have an infection causing them, the reason the cancer is there is because the genes in the cells have started making the wrong proteins. They're making proteins which are not normal. They've got mistakes in them, and those mistakes are of much interest to the immune system, as viruses are to the immune system. And we know this because if we went and take a whole group of patients with, let's say, cancer of the gullet, esophageal cancer, we will find antibodies, signs that the immune system is making a response in maybe 30% of those patients to the proteins that are in the cancer cells. So the immune system is seeing the cancer. It's just not seeing it well enough, because if it were seeing well enough, the cancer wouldn't be there. So the tumors are definitely of interest to the immune system. They're just not doing, the immune system's not doing the job well enough. So that means the tumor is not being well enough seen by the immune system. And there are good reasons why that's the case. Our body's immune system is designed to fight danger. And funnily enough, cancer doesn't look dangerous. Cancer looks like we're trying to repair ourselves. It's cells that are growing and dividing. Infections look like dying cells, because that's what the viruses do. They kill cells. So the immune system sees danger in the form of dying cells. But the cancers look just like something's trying to repair itself. So the body makes the wrong sort of immune response. And the whole idea of immunotherapy is very simple, because it's exactly the same way as the body fights infections. You've got a tumor cell, the little red blobs are the abnormal protein in the tumor cell, and they're taken away to these things called antigen-presenting cells. And if there's danger signals there, I've put inflammation because that's what danger looks like. It's, it's something that looks abnormal and you feel pain and it looks red. If there's danger there, then it turns on the immune system, these green cells, which will then go back and kill the cancer cells specifically, because that's their job. Their job is to be specific and kill only cells that they recognize as wrong. The problem, of course, is that we don't want to be a walking immune system. And if we kept our immune system for every particular virus and bacterium we'd just be one mass of immunity. There'd be nothing else there, because we'd get lots of infections in our life. So the immune system has a process to switch off after it's solved a problem. So you get flu, you make a strong response to the flu virus, lots of cells that will kill flu-infected cells. 3 weeks later, the flu's gone, and all the cells that kill flu have gone as well. And that's the problem, because the cancer, if it were a cancer and not flu, is still there. So the immune system switched on, seen the cancer, and then switched off, and the cancer's still there. So that's what we're trying to prevent. We can prevent it with vaccines, and I'll come to that in a moment. Now, this is the scariest picture I'm going to show you tonight, and you don't probably even recognize it. It's not a banana sliced up into pieces up in the top left-hand corner there. That's actually that bit of your eyebrow up here from a normal person, and it looks completely normal to the person that took it off. You lose that bit of your eye, of the skin on your eye, if your eye gets droopy. The plastic surgeons come in and cut that bit out so you can see again. And the study was done on that particular bit of skin from 4 normal, healthy individuals. And without going through what all the little pictures are all about, what basically they found was that that supposedly normal bit of skin was actually millions of different pre-cancers. lots of little bits of skin cells where the genetic information was significantly damaged. In fact, so significantly damaged that it was more damaged than the genetic information is in a breast cancer, a real breast cancer, so that this bit of skin had accumulated lots and lots of genetic mistakes. Now, that was done on skin. I suspect if you did it on other tissues in the body, you would find the same. That was about a $1.5 billion experiment. That was what it would have cost if it had been done commercially, because they had to sequence the genetic information in millions of cells in there, and each individual clone had to be sequenced lots of times. So that the bottom line was it's not the sort of experiment you'd go around doing twice, but the message from it is that we're all a walking mass of messy mutations in our genetic information. It's just an inevitable process of growing old. But these genetic mutations are the things that our immune system can see and can sometimes eliminate the cells, or the clones of cells that are bad. But if it fails, that's when we get a cancer. So this is a little map showing these genetic mutations. And again, there's more detail there than you want to see, but if you just cast your eye, the further up the picture those sort of black dotty lines are, the more mutations are found in that sort of cancer. And right along at the right-hand end is melanoma, the common nasty skin cancer. It's full of mutations. And it's interesting because that's the one that best responds to immunotherapy. Right along at the other end are tumors like thyroid cancer and Ewing sarcoma, which don't respond to immunotherapy because they have very few mutations, nothing for the immune system to see here. So that basically, it depends what sort of cancer you've got, whether the immune system can fight it well. Cancers which have got lots of mutations are of great interest to the immune system. Cancers with few mutations, the immune system hasn't got anything to fight against. So that's one of the reasons why immunotherapy is not going to be for all cancers. So, is this going to make a big difference? Well, Science magazine thought so in 2012. They described cancer immunotherapy as the breakthrough of the year. Now, why was that? It was because of two drugs, Yervoy and Keytruda, which are now available in Australia for limited indication. These drugs came out of the work done by two colleagues of mine a long time ago, Jim Allison in the United States and Rafi Ahmed also in the United States. They weren't looking for cancer treatments. They were looking to understand how the immune system works. And they discovered molecules that were seen to be very important in switching off the immune system. If these molecules got turned on, the immune system got switched off. And what these drugs are is basically something which, by using an antibody, wipes out those switches so that the immune system doesn't switch off. So that these drugs, if given, as I'll show you in a moment, to cancer patients, can make a real difference to cancer. The only problem with them is, as you can see at the price down at the bottom right-hand corner there, a year's course of treatment with either of these drugs costs $300,000. That's the current going rate. And that's why our government feels rather nervous about this area, because 1 in 80 of us will get a malignant melanoma that spreads, a metastatic melanoma, and that's an indication for these drugs, because there is no other treatment for a malignant melanoma that's spread that's effective. So that 1 in 80 of the people in this country will end up getting a $300,000 course of treatment if we treat them optimally. So that doesn't add up. If you do the sums, you'll work out pretty quickly we'll bankrupt the health system if we do that. So how can we use the immune system? That's one way, the one that science mentioned. And it's based on the idea of taking away the immune system. This is a way of attacking the cancer cells by programming your own killer T cells to go in and kill cancer cells. I'm not going to go into detail on it, but the general idea is you find out what's different about the cancer cell. Let's say it's a cervical cancer cell that's got a viral protein in there, and you make a killer T cell, and you take the cells out of the body, program them to recognize that bit of virus, and then put them back into the body again. And that's called passive T-cell therapy, and it's being practiced right now, and it works very well, particularly for blood cancers, because the blood cancers are easily accessible to the T-cells. Indeed, it works so well that you can't give a really big dose of the T-cells, because the blood cancer cells all die at once. And if very large numbers of cells die inside your body all at once, you get really sick. So they have to do it gradually so that the cancer cell gets wiped out gradually over time and you don't get sick. It's a very effective treatment for limited numbers of cancers, but very difficult in practice, because if you think about it, each of the treatments has to be customized to that individual patient. So it requires T cells from the patient, so you have to harvest cells from the patient. It requires it to be specific for the patient's cancer, so you need to find out what's unique about that patient's cancer. You have to do this all in real time in the lab and then put it back into the patient. So this is another approach, and one which I'll talk about a bit more, where you use the body's defenses against infection by giving a vaccine. And that's what I would like to recommend as a reasonable strategy for cancer treatment. I'll show you how it might or might not work in a little while. But the idea here is simply we identified the cancer antigen. We still have to do that bit, but now we just make a vaccine, put it in, induce an immune response to that, and it will wipe out the cancer, at least in theory. There are no treatments like that in routine use at the moment. And then there's the one that I've told you about, which is taking the brakes off the immune system. That's just a little cartoon to see how it works. But this is the Keytruda and Yervoy in use. And these are the three ways we can use the immune system to fight cancer. And two of them are experimental but work, and one of them is a proven therapy and is now being used. So this is just to give you an idea of how dramatic these T cells can be, the CAR T cells. This isn't, funnily enough, CAR T cells. This is just tumor-specific T cells, but the idea is the same. These are T cells taken out of the patient's body, grown up in the lab, so there's millions of them, put back into the patient. This is a patient with melanoma. It's not brown because this is a secondary tumor that's not pigmented. But that tumor, and then the picture on the right is after 12 days after that patient was given a large infusion of cancer-specific T cells. So it got work done by Steve Rosenberg in the United States. And the tumor just melts away. And this is the sort of response that you get with several of the tumors now with specific T cells. On average, it means that you cure about half of patients if you give them the specific therapy. Half of patients, you do this and there's no response. Even though you've got the T cells right and the tumor's got the antigen, the patient's T cells are not good enough to kill the cancer cell. But for half of patients, it does work. There's a little problem. The graph on the right-hand side is too technical for going through in detail, but what it actually says is that to make room for putting in enough of these T cells, you've got to take the patient's own ones away. So you have to wipe out part of the patient's immune system to make room for the immune system you want the patient to have. And so that makes the treatment a little more complicated. But if you do that, you can get half of the patients with metastatic melanoma to respond to their own T cells and get a cure. The problem with the Yervoy-Keytruda part of the story, which is the second part that I was talking about, is we've got too many targets. Now, these are the targets of Yervoy and Keytruda, two little colored blobs. These are just molecules on the surface of cells that control the immune system. These are all the brakes on the immune system. And there's two of them that we've got drugs against, and there's another 8 there that you can see that are defined already and that we're making drugs against. And we've got drugs against all but 2 of them now. All of these work by different mechanisms. You can add them all together, and they are additive in being able to take the brakes off the immune system and get better immune responses. Each one will cost $300,000 for a course of treatment, and they probably will work better if we give them in synergy. So this is a very major problem that we face. Too many targets, too difficult to use, but they do work. Let's see how well they work. Now this is called a waterfall plot, and I'll have to explain what it is. So that basically you start at point 0 on the graph, the flat line, when you've got a tumor. And then you wait after you've given the drug, and if the tumor is still growing, then the bar for that patient goes up the way, so that the ones on the left-hand side are patients where the tumors continued to grow. If the tumor gets smaller, then you go down the way, and the ones that on the right-hand side have gone down. And the ones right along at the right-hand end are the ones who are totally cured, the ones where it's gone right the way down to -100. So that individual patients are actually cured by these drugs. But you can see that while a lot of patients benefit from the drugs, only a very small percentage of patients are cured by the drugs. And that's one of the practical problems with these drugs, is that we don't know how to pick out the ones that will be cured. And the other part of the problem, which makes it really difficult, is that the little red dots in here across the way, the further along to the right they are, the longer it is before you know whether that patient has benefited. So that if you give chemotherapy, you know pretty quickly that a patient has benefited. But if you give these drugs, you wait weeks, months, and sometimes years before you see the benefit. So these are drugs where you have to give them to a lot of people to get benefit in a few, and it takes a long time to work out whether they've responded, so you have to keep giving the treatment, and therefore it's expensive. So we need to know who's going to respond, and this picture basically says that we can start to use biopsies of patients' cancers to separate out the ones on the right-hand side where they've got the brakes on, and therefore the drugs might work, from the ones on the left-hand side where the brakes are not on, and therefore the drugs are not going to work. And this will be perhaps part of the way we do things in the future. And we can make it eventually into a complicated story where we add up lots of different bits of information about a patient's tumor and work out which drug they will respond to. So we need to do a lot more research in this area. And maybe if we get it right, what we'll end up with is being able to categorize a tumor not by where it is in your body, not by what the genetic mistakes are in the tumor, which we do at the moment, but rather by how the immune system is already seeing the tumor. And if the immune system's not seeing the tumor at all, we'll give a vaccine, and then one of these things to take the brakes off the immune system. If the immune system is being activated, but the activation isn't working in the tumor, then we'll maybe take the brakes off the system. And if they're in the tumor already, taking the brakes off can probably be enhanced by giving something which will kill the cancer cells at the same time. So this is the way of the future with immunotherapy. But I'm interested in this sort of a therapy where you give a vaccine. And I'm interested in it because we can use it to fight cancers caused by papillomavirus, the virus I'm interested in. And one example of that would be not cervical cancer, which you've all heard about, because we've got a vaccine to prevent that now, and there's a lot of people immunized in this room, I suspect, but rather cancer in the throat, oropharyngeal cancer. Now, this is a common enough cancer. It can be caused by smoking or by drinking too much alcohol, but there's another cause for it, and that's papillomavirus. And this guy is promoting it by drinking, that's Vladimir Putin. But this guy, Michael Douglas, went out there and told the world how he got it, and he got it by oral sex, because that's how papillomavirus gets into your mouth. His publicist reversed that story the following day, didn't think it was a good image for the guy. But it's actually a very common cancer, and commonly caused by papillomavirus. That's Babe Ruth, he got it. That's George Harrison, he got it too. And that's Sean Connery, and he got it as well. And that's Rod Stewart, and he got it too. A lot of Scots in there, notice, but never mind. It's a very common cancer. Now, this is one way of treating papillomavirus infection, which I don't recommend, but it's a little bit worrying that 560 people on Facebook actually do recommend it. It would be very much better if we could find a better strategy. So we, a long time ago, worked out a vaccine to try and treat papillomavirus infection based on the virus proteins that were in there. And we developed this with CSL nearly 20 years ago, and we did a trial, and we got all the immune responses that we wanted. It all looked really good, except it just didn't work. The patients were no better after we'd given the vaccine than they had been before, which was very disappointing because the same vaccine had worked beautifully in mice. But mice lie all the time. So we made another mouse model where the mice didn't lie quite so much because the vaccine didn't work in this model. And I'm not going to go through all the details of it with you, except to say that it's a model that better mimics the cancers that we're trying to treat. And what we found with that was, first of all, the picture on the right is a picture through a mouse ear, and that big purple blob at the top is the pre-cancer, if you like, that these mice get. That's thickened skin caused by the virus, but it's also pre-cancer. And we spent a lot of time trying to work out whether we could get a treatment that would make grafts of that skin come off a normal mouse. And the short answer was yes, eventually we did. What we found was that the graft, the skin that had the tumor in it, if you like, was attracting the immune system, but the wrong sort of immune response. Because if we took the skin off a mouse that had the tumor but had no immune system and grafted it, then the recipient mouse could get rid of it quite well. But if we took it from a mouse that had an immune system, the immune system was making the wrong sort of response and stopped the graft coming off, which was very annoying because we were really not trying to get that effect. And we spent a lot of time working on this, and what we showed was that there are a lot of cells in the skin there, in the tumor, T-cells, killer T-cells supposedly, but they weren't. They were actually cells that were suppressing the immune response. They were these cells that switch off the immune response. And we spent a lot of time in the mouse model working out what they all were, and they've got names, and I'm not going to go through them all. But the nice thing is we found a solution to the problem, so that by extracting these cells from the skin, and they're called NKT cells, it doesn't really matter what they're called, we could actually get the grafts to come off, so that a graft which was from a mouse that had the thickening of the skin and a normal immune system stayed put, but the one without these particular cells that were causing the problem came off. Great, we've solved the problem. Well, not really. We found another 6 different things that stopped the cells and stopped the immune system working in those grafts. And each of these is work done by one postdoc in the lab over 3 years solving one problem. And at the end of that time, we had 6 new problems that we had to solve before immunotherapy was going to work. Good for the student, they get lots of papers out of it. Bad for the treatment, because it means we've got more problems to solve. And unfortunately, everything that we found in the mice on this occasion, the mice didn't lie. It was also true in the cervix in women with cervical cancer. So that everything that was bad in the mice was equally bad in the human, and therefore still a problem that had to be overcome. So obviously, if cure is difficult for papillomavirus infection, we'd better try and prevent it. And of course, you've heard about the cervical cancer vaccine, which was possible because Harold Zerhausen found out that cervical cancer was caused by papillomavirus. And Jan and I came up with a vaccine which is now available as Gardasil and Cervarix. And because that makes money for the University of Queensland, I've got to make a declaration of conflict of interest. My Vice-Chancellor is very interested in how much money the vaccine makes for the University of Queensland. To distract you from the thought that I might also make some money off that, I'll remind you of what the Australian magazine thought of me in 2006. I think it was probably the vaccine they were talking about there. But I'll also point out that you don't always get the nice stories. This is what Cosmopolitan magazine had to say about me. Tant pis, as they say in French. But the vaccines work, and that's the major. I don't mind what the Cosmopolitan magazine says about me. We've got a vaccine that works. It required tens of thousands of women to prove it worked, but we have a vaccine that's very effective, and we've managed to get it out there. This was all the stuff that had to be done. It took 15 years to get it out there. Work done by many different people. I know I get a little of the credit for this, but in fact, there's a lot of people should be getting credit for the vaccine being out there. And the challenge is still the public education bit and making sure it works out there in the real world. We now have better vaccines that are able to prevent 9 of the viruses that cause cervical cancer, not just 4. And we have a really big challenge getting it out where it's needed. In Australia, what's happened with the vaccine is that one disease caused by papillomavirus in the genital tract has gone away. Genital warts in young women have just disappeared over the course of the last 10 years since the vaccine came in. The green line shows what's happened in the under 21-year-olds who were vaccinated. The dotted green line is what happened in the over 30-year-olds, no change. So basically, genital warts have gone away in the women that were vaccinated. And really interestingly, they've also gone away in the men, and they were not vaccinated. It's gone away in them because of a wonderful thing called herd immunity. Immunize enough people, and the disease can't spread anymore, because you're only able to pass it on to someone who can catch it. If they can't catch it, they won't pass it on. So that both men and women are now protected. And I was used to do trials in treating genital warts. I can't find any patients to treat now, which is nice. And it's gone away from the pap smears as well, the same viruses. This is pre-vaccine, 20% of pap smears had these nasty cancer-causing viruses. 5 years after the vaccine's introduced, it's down to about 4%. And now it's gone completely. Good trick, that. But the latest data is that it's really gone away. It's 90% down in all under 30-year-olds. And that's really a good sign that we will get rid of cervical cancer within the next 20 to 30 years in this country. But the problem is global usage, and I'll finish on this note. I started on a public health message, I'll finish on one. The green colours on the map there are where papillomavirus vaccines are used routinely. The purple blobs on the map there are where cervical cancer kills women. They don't match, do they? And that's the real challenge. We need to make sure the vaccine can get into the developing world where the cancers are. So the little red circle on the right is Vanuatu, and we're doing projects there to deliver the vaccine there. And without making a big deal out of it, Vanuatu is a challenging country. 1 in 100 women walking the streets in Vanuatu today has cervical cancer and doesn't know it. If we go out and survey, that would be the equivalent of going around this room and finding 2 cervical cancers in this room just by testing for them. And another 4 in every 100 are going to get cervical cancer because they've got pre-cancer now. It's a country with very few doctors and a very large number of parliamentarians, a very bad ratio that. You want to try and get a better ratio of doctors to parliamentarians than that. But more importantly, there's no vaccine infrastructure to deliver vaccine effectively there. And so we demonstrated that if you want to, you can deliver the vaccine there. A standard picture of 3 girls, one looking very happy because she's already had the vaccine, one looking rather uncomfortable because she's just had it, and one looking rather nervous because she's about to get it. But the point is that with education, and this is the education program going on in the north of Afati Island in Vanuatu, with education, you can get the vaccine just as well delivered in the developing world as you can in Australia. In fact, if anything, somewhat better. The 10 to 12-year-olds, we managed to immunize 80% of all the girls in the Fatty Island in 1 year, and 93% of them got all 3 doses of the vaccine. In Australia, we managed perhaps 80% of those who chose to come and get the vaccine. Only 50% came back for the 3rd dose. So we can deliver the vaccine there. The challenge is simply to make sure that the vaccine is available. And if we get it available, we can get success. So the conclusions from what I've said to you is that we can use the immune system to fight cancer. We have checkpoint blockade inhibitors. They're here and now, and they work. They're expensive, and they only work in some patients, and we can't predict which ones will get the benefit and which ones will not. Specific immunotherapy works beautifully to cure mice, and unfortunately, as yet, is not a cure for humans, but we're working on that. And the reason for that actually turns out to be the story I told you right back at the beginning. All of these mechanisms that defend the cancer turn out to be mechanisms that are switched on to defend newly repairing bits of tissue from being destroyed by your own immune system. So we're trying to overcome a physiological hurdle. Something that's there to protect us is actually helping the cancers to grow, and that makes the treatments rather difficult. So the bottom line is, it's better to go out there and protect yourself against cancer, remember the messages for public health, and then think about vaccines against the viruses and bacteria that cause 20% of all the cancers that we get in this country. And they will always be better than a very expensive cure. Thank you very much for your attention.
Thank you, Ian. Now we've got time to do a Q&A.
My question is, how much do we understand about the dynamics of what the viruses actually do? We're looking to kill the viruses, but do we understand what actions the viruses are taking in cells that then lead to the multiplication of cells?
It's a good question, and for some of the viruses that promote cancer, we know that quite clearly. Papillomavirus is it's very simple. If you're a virus, you have only one job in life to do, and that's to make more viruses. Nothing else. It's very boring otherwise. They can't watch television, there's no football. So what they do is they have to make as many copies of themselves as they can. Now, the papillomavirus can only copy itself at the same time as the cell it's got into is dividing. So the best strategy for the virus is to make sure the cells divide a lot. So the program of the virus is change the program of the cells they infect to divide a lot. And eventually, that's what a cancer is, cells that divide when they shouldn't. And the virus is sneaky because cells have got programs to stop them being made to divide inappropriately. It's a good idea, it keeps you healthy. But the point is the virus also has a booby trap which switches off those mechanisms. So one part of the virus makes the cells divide a lot, and the other says, don't die even though you ought to die to the cell. And therefore you get this effect of the cancer growing. And eventually, lots of divisions mean more chances for mistakes in the genes, and therefore more chances that the thing becomes a permanent cancer rather than just dependent on the virus.
Another question up the top here.
My name's Claire Geisler. Thank you for your talk. If you have proved that immunotherapy has been now a new device to actually help the body, why can't we work out why our immune system cannot protect us in the beginning? That we can actually prove that we can give what we need to the body to stop it even happening in the first place?
Yeah, it's a good question. I mean, why is it that we don't all just use our immune system to prevent us getting cancer? That's a more complex question. The answer is probably most simply put by saying that if you're a cancer cell, you have this enormous capacity to change what you look like. So that many cancer cells start off being of interest to the immune system, and the immune system will try and kill them. But as time goes by, the cells change and they escape from the controls that the immune system put on them. Can I give you a practical example of that? If you have the misfortune to need a kidney transplant, of course, you get your kidney from another person. And in order to accept that kidney, you have to have your immune system switched off a bit because that person's kidney is a bit different from you. Now, there are many cases, not hundreds, but many cases worldwide where a kidney has come from a donor who had cancer many years previously and was cured of it. And then the kidney was given to somebody, their immune system was switched off, and the cancer in the kidney grew out of the kidney. So these cells had lain dormant, controlled by the immune system for many, many years until the immune system was switched off. So that the immune system sits balancing with the cancer, if you like. It can't kill it, but it can keep it under control. But if it's damaged, and as we get older, our immune systems gradually fade. I hate to say this, but you're actually rather old immunologically after the age of 12. So that then after that, the immune system's all downhill and you're more likely to get cancer. I don't know if that answers your question, but it's certainly part of the answer.
Thank you for that explanation. But if we are all told that we have cancer cells in us, no matter who we are, that seems to be a given, that the medical fraternity says you are carrying cancer cells all the time. It's the fact that some people have switched on and some people don't. What is it that we can do with our immune system to be educated? As you say, it's better to prevent rather than cure in terms of cost.
Well, we want to look after our immune system, don't we? And it's no surprise, because I've already told you this. Smoking is bad for your immune system. Alcohol is bad for your immune system. Obesity, funnily enough, is also bad for your immune system. So all of the things that are bad for putting you at risk of cancer, that's not the only reason they cause cancer, but each of them turn your immune system off. And unfortunately, getting old is bad for your immune system too. And that's something we haven't yet found a cure for. But I think the reality is that, remember, it's really not a good idea to have an extraordinarily powerful immune system. Think about this. One of the consequences of having an extremely powerful immune system as a woman would be that you would be unable to conceive and carry a child, because your child is half not you. It's your partners, and they're different from you, so that the whole immune system switches off at puberty to enable conception to occur effectively. By the time you're 10 or 12, you've seen most of the nasty viruses you're going to see. You've seen most of the nasty bugs you're going to see. So you've got a programmed immune system, and what you don't want is to start making new immune responses then. Unfortunately, most of the cancer cells come after that.
Thank you.
Another question down the front here. Thanks, Cara.
There is some evidence that a certain amount of viral DNA is passed through generations. It gets into the DNA and stays there. Have you got any opinion about whether that part of the DNA may be reactivated and be a cause of cancer in humans?
Yeah, look, there's clear evidence that we inherit not just viral DNA from our parents, but bits of DNA that come in across the placenta, not just the ones that we inherit genetically. So you can actually have cells which are entirely derived from your mother, and not just half derived from your mother and half from your father, but entirely derived from your mother. And you can certainly carry virus genes across that way. I don't know of any direct evidence that they promote cancer. I can think of one or two arguments from the papillomavirus story to say they probably don't most of the time, because if that was the predominant route by which you got the virus, of course the vaccine couldn't work because you've already got the infection before you get the vaccine. And the cervical cancer vaccine only works if you've not had the virus yet. But we also do know that some transmission occurs that way of the virus from mother to child, because there's a disease called juvenile laryngeal papillomatosis, which is an extraordinarily long and difficult word to say and spell, but is basically a precancer lesion in the airways of the children of mothers who have had papillomavirus infection. And the virus there is clearly not being passed sexually, and there's not even direct evidence that it's passed mother to child outside the body. It seems more likely that that occurs in utero. So yes, there is the potential for that. I don't think that's going to be the answer. Very few cancers model as having a high heredity factor. In other words, they're not obviously transmitted mother to child in the way that you'd expect if that was a predominant way of spreading cancer.
Okay, the lady in the middle here. We've got a Kara, would you mind? Thank you.
Thank you for your talk. I'm just wondering which cancers at the moment are most responsive to the immunotherapy treatments that are available?
Right. Well, the list is growing week by week, but what we recognise at the moment first of all, in terms of the cancers that best respond, interestingly enough, the one that best responds is a cancer of the immune system called non-Hodgkin's lymphoma, and nearly 60% of patients with that disease will respond to one or other of the two drugs that I mentioned. The others that are responsive, well, melanoma is top of the list. Whether that's just because it's the one which we have the most data on, I wouldn't like to guess, because melanoma has always been recognized as a cancer that gets better with immunotherapy. But also lung cancer, not the one that's associated with smoking, but the one that's more common in people who have not smoked. Kidney cancer, and increasingly almost every other cancer that's tried, so that the running rate is about between 20 and 30% for lung, kidney, and melanoma, and between 10 and 20% of patients with otherwise uncurable cancers of almost every other organ that's been tried. Not every cancer, I regret to say, but a large part of cancers. And the companies are obviously doing more and more studies to find out where these drugs work. I should point out that they're notwithstanding the pain in your pocket that comes from these drugs, they have side effects. They're not entirely benign, because turning on your immune system, of course, can turn it on against bits of you that are yourself, and you can get there for autoimmune disease as a result. But particularly Keytruda, which is the more recent of the two drugs, seems to be relatively free of side effects at the doses that are commonly given now. So that it's more a case of you have to wait a long time to find out if you're going to get benefit. But I have seen patients and friends of mine who have had melanoma and have been covered in melanoma, and they get the drug and you see them 6 months later and there's not a sign of the tumour left. And when you see it working, it's really dramatic. I mean, it's not sort of, it's not just the patient feels a bit better, the disease goes away. So we're going to see a lot more trials going on of these drugs. It's licensed in this country for treating melanoma that's spread, and at the moment that's its only official use. But there's trials going on in almost every other cancer you can think of.
We have another question just here.
Yes, good evening. I'm very impressed with the research you and your fellows do, and I'm actually blown away by that. But can I please draw attention to the last thing you said about prevention? How all the factors which we actually, a part of our lifestyle, which actually encourages the problems that you're trying to solve. Instead of us trying to find a solution in other people's pockets, if we looked at our own lifestyle, we could actually make huge changes It bothers me that I spend my time with a lot of different groups, university students at night, go out to dinner with them. I'm the only one who eats the greens. They're spending the entire evening floating in alcohol. The obesity factors, and people just say, look, I feel happy, forget it. Yeah. Well, of course, the tumours don't forget it.
Yeah, look, it's really hard to persuade people to change their behaviour, particularly when the connection between the behaviour and the consequences is remote and not 100%. Everybody knows the 102-year-old who smoked 40 cigarettes all their life and never got cancer, and the guy down the corner who obviously consumes half a bottle of whiskey every day and seems to be perfectly healthy at the age of 80. But what they don't see is all the other people that got into trouble, and the message doesn't get out there right. We're free people. We can make choices. We need to make educated choices. I think the Jesuits were the ones that worked out, get a child by the time they're 5 and you've got them for life. So the really important thing is to get the public health messages out, not to 20-year-olds who are invincible and will live forever in their minds, but to 10-year-olds who can be educated and maybe will adopt a lifestyle. It's interesting to watch my kids because they've grown up through the era where we've known about these things, and they don't smoke, their friends don't smoke, they don't drink much alcohol, they maybe have the odd drink now and then. They don't drink like I drank when I was a student. I'm not saying something, but you know, they perhaps have better education now, but that message is not getting out generally across the community. I mean, the consumption of alcohol is still steadily increasing in this country. Tobacco is only going down because the Treasurer knows the very best solution to tobacco problems, and that is to keep increasing taxes. It's the only measure that works for controlling smoking. Everything else fails. It doesn't matter how much education you do, how many warnings you print on packets. It makes no difference whatsoever at all. But increasing the cost of cigarettes always reduces consumption anywhere you do it in the world. So maybe we have to use fiscal means to do it. It's hard, but it works. But I don't know if a fiscal means it'll increase sprout consumption. I'm sorry. All I can remember about sprouts is what they were like at school when I had school dinners and were reduced to green pulpy masses which we carefully pushed to the side of the plate. But yeah, look, we obviously ought to adopt as healthy a lifestyle as we can, or be prepared to accept the consequences. But I'll just put one note of caution there. You know, you don't want to live forever. I mean, there are certain aging processes that go on that are irreversible and unavoidable. And I would much rather die falling off a cliff while skiing when 80 while still healthy than gradually decline into senescence over the 20 years after that. So everyone their own poison. You know, cancer is not painless, but it's a relatively quick death. No, I'm not advocating the chloroform measure, I promise you that.
Now, I'm sorry, we will have to finish our questions there. Sorry, we do need to move on, but I would like to ask David to do the vote of thanks, and again, thank you, Ian.
Ian, thank you for not advocating chloroform. Thank you for taking us on a 125-year journey from Cooley's toxins through to the understanding that a clinician who understands his patients can actually make a significant contribution to not only the curing of cancer through the modulation of the immune system, but the prevention of cancer as well, and for giving us the hope that what was incurable may still yet be intervened and dealt with in our lifetime. Dr. Fraser, thank you very much.